Designing a scissor window winding mechanism with CEAD. We use the constraint-driven engineering design synthesis methodology in the first step. Here we are importing a car window as a rigid group and then the scissor mechanism as a flexi group, which contains the pinion sector as a driving mechanism and scissor links supporting the glass. We give a configuration specific dimension, height, and then make a copy of the entire mechanism. The goal is to arrive at the scissor linkage dimensions that satisfy both window closed and window open configuration. We will now change the dimension variable ht to configuration specific variables closed ht and open ht. Let's output the scissor link dimensions using text to track them during the synthesis. The current scissor link dimensions S1 and S2 are 490 and 435. We already know the height in closed and open configurations, which are the boundary conditions. So we first use step-by-step optimize to bring the height dimensions close to the required values and then fix them using equations. The closed height should be 500 mm. Notice how the scissor link dimensions are changing as we define the two configurations. At the end, we have the linkage dimensions that satisfy both the closed and open configurations. This is what we call constraint-driven engineering design synthesis. Force calculations. Here we compute the effort needed at the end of the lever to lift the glass. To do this, we create a new force configuration, then take individual links of the mechanism and create free body diagrams for each of them starting with the glass. The primary force acting here is the weight of the glass, which is 4.5 kgs or approximately 45 newtons. Since the weight acts downwards, the vertical component is given as -45 and made constant. The two reaction forces act at the points the scissor links meet the glass. To calculate these reactions, we give the equilibrium conditions as equations. The first equation is sum of all forces must be equal to 0. Then we create distance vectors and give moment equilibrium conditions, that is, sum of all moments about any point on the link must be 0. Once the equilibrium conditions are given, we have the reaction forces. Similarly, reaction forces for the left and right link have been calculated by giving equilibrium conditions for each of them. Now we have the sector tangential force, which is 168 newtons. Pinion tangential force is exactly same as the sector tangential force in the opposite direction as per Newton's third law. The effort at the end of the lever is proportional to the pinion tangential force. The constant of proportionality being the ratio of the pinion radius to the lever length. Lever end effort is 24.13 newtons. Simulation. We now simulate the mechanism on force configuration to see how the effort needed changes as the height of the glass increases. To do this, we export this data to Excel during simulation and then plot a graph in Excel. While simulating, we can see that the whole mechanism is updated, which includes the lever, sector, scissors, glass and the reaction forces. We can now use the data in Excel to plot a graph to see how the effort needed changed as the height increased. Thank you.